In statistics, normal distributions are extremely powerful tools that we can use, and we will base almost entirely the latter half of the course on talking about normal distributions. In the first half of the course, at the very beginning of the course almost, we talked about the empirical rule that said if we have a normal distribution and we go out one standard deviation on either side of the distribution, that's 68% of our data. Two standard deviations, 95%. Three standard deviations, 99.7%. It turns out there's even more powerful stuff that we can do with these normal distributions, and we will tap into that in this chapter, or we'll begin to, and then we'll apply the principles of this chapter to what we'll do in chapters 7, 8, and 9. So all of these chapters are going to be based on really understanding what the normal distribution is all about. It's very important stuff. I would say this might be the most critical ideas that you'll learn for the course because it's the foundation that we'll build the future chapters on. So the first thing you're going to do in the problems in this section is that you're going to draw a curve, and I can't recommend drawing a picture highly enough for all of the problems in this chapter. So all of the curves look the same. You've just got this nice normal bell shape, and I always draw the axis with it. And then you're going to label stuff on the axis and shade it. I don't have this one shaded yet, but we'll look at pictures with them shaded. And then we're going to whip out our handy dandy calculator, and we're going to use two calculator functions, NormalCDF and InvNorm, to calculate stuff for us, and that's just going to be really cool. So first, draw the curve. The curve always looks the same. It's this bell shape. Doesn't matter if you do a perfect picture or not. I've tried to get a pretty close to perfect picture here, but when I actually draw, it's not perfect at all. And then we are going to label and shade. You always want to label the mean, and the mean is always smack dab in the center of this curve. And then you can label negative infinity and positive infinity. It turns out that our calculator doesn't actually have an infinity, and so we use the biggest number that we can put in that calculator. 1E99 is actually scientific notation. I'll show you how to stick that in the calculator in just a second. And that means that it's a 1 followed by 99 zeros. So let's see, 1,000 has 3 zeros. A million, I think, has 6 zeros. A billion has 9 zeros. A trillion has 12 zeros. This is like way more than a quadrillion or a septillion or anything that you could possibly imagine. These are enormous numbers. And so that's what we'll use for positive infinity, and we'll stick a negative sign in front of it for negative infinity. And then here is how we decide which calculator function to use. So I think of the black line that's right through here, that's the flat horizontal line, the only black line on this drawing. I think of it as a belt. So, and particularly if you think of belts, they are also horizontal if you're standing up, which hopefully most of the time you are. So you've got this belt across the midsection of the graph that's just like a belt across the midsection of the body. And then I use an analogy, a mnemonic, to try to help remember. In normal boxing rules, and NormalCDF normal boxing rules associate the two together, you are allowed to strike above the belt. Anything above the belt is acceptable for normal boxing rules. So all the orange stuff, if we're trying to compute it, if we're trying to label something and compute the area under the curve and see how the area under the curve is shaded in orange, all that orange stuff we'd use NormalCDF to compute it. And it turns out that this NormalCDF computes the area under the curve between two shaded values. And you can stick negative infinity in one of the minimum for the minimum, or you could stick positive infinity in for the maximum, or you could stick two actual data values in there. And then if we wanted something below the belt, inverse means opposite, essentially. And so if we do inverse norm, that's the opposite of normal boxing rules. And striking below the belt is the opposite of normal boxing rules. So if we wanted to find a data value or a z-score, we would label it down here at the bottom. And anything that we want to use to calculate stuff here at the bottom in blue is going to use inverse norm. So it'll take some different inputs, and it's a different calculator function. So again, if what we want to find is area under the curve, and by the way, area equals probability, area equals proportion. Area is always between 0 and 1, just like probability and proportions are. And then if we want to find percentage, we just multiply by 100% to find percentage. Okay, so let's look at some actual problems and do this stuff. We're going to look at several problems all under the same scenario. I'm going to use the midterm exam as our scenario, and we are going to assume that's not actually true. The mean and the standard deviation are true, though. We're going to assume that our midterm exam scores are normally distributed. So there are lots of things that are normally distributed, but not midterm exam scores usually. But we're going to, for our purposes, assume that our midterm exam scores are actually bell-shaped, normally distributed. And that the mean, and this is actually true for online last term, had a mean of 77.5, rounding to 3 significant digits, and a standard deviation of 11.5, rounding to 3 significant digits. And so we're going to use those. We probably should have done more significant digits, but I thought that would be a nice example. So here we are asked the question, what percentage of students are earning an A? And so earning an A, that would be 90 or more. Really, it would be 90 to 100, but we're going to go ahead and say 90 to infinity, assuming there can be extra credit and all that jazz. So 90% or more, we're going to compute the proportion and then multiply by 100% to get to percentage. And so here we bring up our calculator to get to the NormalCDF function. We will do second and DISTR. And notice that the NormalCDF function takes in, this is written on your formula card, by the way, the minimum, the first entry is the minimum of the shaded region. And so here we have our shaded region, and our minimum is the left, the thing on the left of the shaded region. And that's going to be 90. So we'll do second DISTR, and then option 2 for NormalCDF. And then we're going to put 90 in here for the minimum. And then the maximum is 1E99, which represents our infinity. So that's where we got it. So 1, and then the E is second, the second key, and then the comma key that's right here above the 7. So second and then comma. And notice how this E is shorter than the 1, and it'll also be shorter than the 99. And if your E is not shorter, you're using the alpha E, the wrong E, and you'll get the wrong answer. So definitely make sure you're using the right key, the right E, second, and comma for this one. And then for the mean, 77.5 was our mean, and 11.5 was our standard deviation. And then we just paste all of this into the NormalCDF function. And again, we're using NormalCDF because the thing that we want to find is labeled above the belt. And so enter, and then times 100 to convert this to percentage, and that does all our work for us. And so if this were a normally distributed curve, then we would have seen 13.9% roughly of our entire class would have earned A's on the midterm exam. Woo! That's pretty awesome. Really, I think these scores are really good. I'm excited about them. And then let's look at a different problem. Okay, let's see the probability, no longer percentage, so we're no longer multiplying by 100%. This time we want the probability that a randomly selected student will be earning a D. And a D is between 60 and 70, so we've got our shaded region here, 60 to 70, and our minimum and our maximum of our shaded region is now 60 to 70. Again, because we're doing probability, percentage, and area under the curve are all above above the belt, so that's all normal CDF. And so let's bring our calculator here and do this one. So second DISDR and option 2 to get to normal CDF, and then 60, 70, 77.5, and 11.5, and just paste all that into and we get 19, or well, 0.193, but that would be roughly 19.3% if we had done it in terms of percentage. But the probability that a randomly selected student would earn a D would be 0.193. And then our final problem that we want to work on is going to be something that's below the belt. So let's say we wanted to find the 90th percentile. And here that means what is the data value at the 90th percentile. And if you're doing the 90th percentile, then that's really good, because that means that 90% of students are scoring less than you scored. And only 10% of students are scoring better than you scored. So that's a really good score if you're doing the 90th percentile. So to do any data values, actual data values, we label them below the belt. And anything we label below the belt is the opposite of normal boxing rules. And so that means we're going to use the inverse norm function. The inverse norm function takes in area to the left. By the way, if we were given 15% or 20% as the area to the right, or even 90% as the area to the right, we would have to subtract that from 1, because this has to be area to the left. I'm going to try to do an example in the chapter 7 video where we actually have to do that, but I'm not going to do one here. But you don't always just put in what it tells you in the problem. So sometimes you actually have to finagle, because this always has to be area to the left. You have to sometimes finagle that. So second DISDR, this time we're doing option 3 because it's inverse norm. Our area to the left is 0.90. Our mean is still 77.5, and our standard deviation is still 11.5, and we paste all that in, and we get a score of 92.2. So if a student earned a midterm exam score of 92.2, that student, she would be at the 90th percentile. And so hopefully this helps a lot understand how to use your calculator functions, and more importantly, how to do the whole process of drawing the curve, labeling. Notice how we labeled the mean on every single one of these. Also notice how we labeled the relevant data values. Earning an A is 90 or more. Earning a D is 60 to 70. The 90th percentile means that 90% is to the left, and we're trying to find this data value right here that has 90% below it. So notice how we've drawn the curve, we've labeled and shaded everything, and then we choose which calculator function based on whether it's above or below the belt, and we actually go through and calculate everything by putting the right inputs into normal CDF and inverse norm. So hopefully that's got you there, and you'll be good to go.